Yeah. So this angle is same as the angle here. So now I use the same thing here. So for positive sequence, you can write it the same way. So this is our positive sequence angle, and I write the positive sequence angle here. And this is our positive sequence magnitude. I write positive sequence magnitude. Is that okay? So you can do this derivation, and I think you have already done it, maybe when you're doing exercise. And then for the negative sequence, so this is for positive sequence. For negative sequence, let's do some trick. Let's do some tricks. So what you can do is you can do your regular math, but I would like to do some tricks now. So the main difference in positive and negative sequence is the phase sequence. You have positive here. So you have positive here and you have negative here. And for the third phase, you have negative here and you have positive here. So if I can make this positive as negative and this negative as positive, then I can use the same expression, right? How you can do that? Just take the minus common.
Okay.
Yeah, you can just take the minus as a common. So what can you do is, so you can write negative sequence, let's say negative sequence, a negative sequence as fa minus cap cos omega t plus phi naught minus. What I do now is I write it like this: minus omega t minus phi naught minus. Is this okay? And you know that the cos minus theta is equal to cos theta. Is this fine? Yeah, we of course have t here. The same way, fb minus, so I have to check the notations again. So it is f minus, this is also f minus cos omega t plus phi naught minus, and then is it phi naught minus? Okay. And then this is plus. So I can write it like this: minus omega t minus phi naught, and then minus 2 pi by 3. Is this fine? And the same way I can write my c. Okay. Now, does it look like positive sequence phase difference? Like the first phase does not have any phase difference, second phase minus 2 pi by 3, then the third phase 2 pi by 3. So in alpha beta frame, alpha beta minus, let's say, can I write it like this? E power j into minus omega t plus, sorry, not plus, minus phi naught. Is it okay? Using the same structure for positive sequence? Yeah?
Yes.
So if you know how to derive positive sequence, you already know how to derive negative sequence. So you do whichever math, you will get this result. You do? So how many of you tried and got the same result for negative sequence?
Yeah, right. But I did what math.
Yeah, that's okay. That's okay. So if you do a lot of math, like the basic maths also, that's also fine. But I just don't want to do those maths,
Yeah.
I'm a little lazy doing those maths. So what we can write is, we can write f minus e power j minus omega 1t minus phi naught minus. Is this fine? Is this okay?
Yes, sir.
Okay, cool. So now if you know this one, then and then of course your zero sequence you see in only zero sequence. So your F0 would be your F0 basically, F0 cap. So you see zero sequence only in zero sequence. So now if you know your alpha beta frame component, so this is your actual alpha beta component. So this is your alpha beta positive sequence, alpha beta negative sequence. So you can write like positive sequence cap into positive sequence angle. So you can write it like omega 1 t plus phi naught plus, and then f minus cap e power j minus omega 1 t minus phi naught minus. Okay. And you already know how to do dq transformation. So f dq is basically your f alpha beta into e power minus j. Which angle did we use for transformation? So we used omega 2, it's theta p, right? So let's use that only. So it's so theta p, and here your theta p is equal to omega 2 into t plus plus the gamma naught. Yeah. So you can simply solve it again, and I'll just write the final answer. You would get like j omega 1 minus omega 2 into t plus phi naught plus minus omega naught, gamma naught, and then plus your negative sequence, and you can see it is your minus omega 1 plus omega 2, and then we have minus phi naught minus plus gamma naught. So this is the final answer you should get. And of course, you do not want to see your DQ in a complex vector form. You want to get matrix, then you can just solve this equation and then you get your matrix. And I think you know how to get matrix from this, right? We did it for getting the part transformation matrix from this. Okay. So this is the final expressions where you have positive and negative sequence components. And if you understand this, then you understand everything about transformation. If you just understand this equation, because this is very important equation, and this tells you whether you will have harmonics into the DQ frame or not. So we learned the cases, right? We learned few cases. So like now you can see that if your omega 1 and omega 2 is same, if these two are the same, what happens is your FDQ would be, just this term, e power j phi naught minus this plus e power minus j. So I'll just take minus common, so it will become 2 omega 1 t and then plus phi naught. Yeah. So you see your positive sequence has become DC. This is the DC, and this is your AC. And what's the frequency? It's a double the frequency. So frequency, let's say frequency DQ is your double the positive sequence frequency. So if F1 is your 50 Hertz, then you get in DQ frame which frequency? 100 Hertz. So when you have the negative sequence in your 50 Hertz system, then you see DC also because of positive sequence, and you see 100 Hertz component for negative sequence. If you do not have negative sequence, then you just see DC. So in your exercise, you have simply done with the positive sequence. You have not done with the negative sequence. But try to add negative sequence, you would see these harmonics also. Okay. Yeah. So in case you want to filter out, let's say there is a negative sequence and positive sequence and you want to filter out. You want to just filter out the positive sequence. Then what's the simplest thing you can do? The simplest thing. If you want to find just a positive sequence in the DQ frame, very simple.
I have to add this component.
Yeah. You can subtract that component. That's also there, one thing, but very simple thing. You know, one is DC, one is AC.
Yeah, the mean value of the
Yeah. The simplest thing, find the mean value. The simplest thing, you find the DQ component. Of course, there will be AC. Find the mean of that. You get the DC value, right? Or you can do the low pass filter. So the low pass filter with the bandwidth, less bandwidth. So that also gives you the these things. But that's a very simple thing. But there are advanced things also to do it. There's a DDRF. There's a double decoupled synchronous reference frame. There's a ZOGI. There's so many things you can do. But this is the very simple thing you can do. So,
I have a question. For the FDQ, for the DQ frame, I'll just derive now the one in the rectangle. Is the negative sequence, is it minus, F minus cap exponential J into brackets minus W1 plus or bracket minus into bracket W1 minus W2T?
I could not get it. You want to say some equation?
Yeah, I just want to clarify for the negative sequence,
Mhm.
negative cap. For the Euler part, is it minus into bracket W1 plus W2, or is it minus W1 minus W2T?
Yeah, they both are the same.
Ah, okay.
Yeah, so here I just took the minus common.
Okay.
Yeah. Yeah. So, yeah, so whenever you have some doubts, feel free to ask questions. And because I'm basically here to help you, so not help myself. So you should ask even the smallest questions you get. So don't feel like anything. So that's my favorite part. When you ask questions, I also feel like, okay, there are some questions, people are listening, you know? Okay, cool. But is this clear? Okay. So let's check these things. And for example, if you have two positive sequence with different frequencies, but before going there, we would like to see some more graph. Okay. So I would like to use this graph itself. So I don't know whose MATLAB script is this, but let's use it. And I'm going to add some negative sequence in this. Okay. So let me add it very quickly. So, oh, okay. So like there is a button, the power button beside, and I clicked it by mistake. So I would just copy this. So the very first thing is to get familiar with your MATLAB script so that we can, and you can use this to test your things. So we make this positive, we make this negative, and I make this as negative. And I give one variable. Let's say 10 times of the positive sequence magnitude. Okay. So now we have positive sequence, negative sequence in the system, and the negative sequence has 10 times the magnitude of the positive sequence. So what do you expect? So in DQ frame, what do you expect? You expect DC or AC or both?
Both.
Both. And
AC.
you will get AC only?
AC. AC.
AC only? You have positive sequence also, right? So for the part transformation angle, where do we use it? It's here. So I'll just put it on the top so that we see it. And I would like to change few things here. So let's say theta positive as this. And I use this theta positive here. Is this okay? I just changed the variable. And the theta p, so one moment, I cannot use this the same, I just make it capital. So this is our positive sequence angle. Okay, I can make this POS, maybe it's easier. It's positive sequence. And then you have, this is part transformation angle. So now the part transformation angle, I make the same as, for part transformation angle, I make same as positive sequence angle. Is this clear? So what it means? It means our omega 1 is equal to omega 2. And your phi naught plus is also equal to gamma naught, right? Yeah. And I think it's not very visible. So what I do is I change the display setting. Is it more clear? It is better than previous. Okay. So yeah, so in this case, so you said it will be only AC, right? Yeah, you are wrong. It will have DC also. Why it will only have AC? If you have positive sequence, it will positive sequence fundamental, then it will have DC also, right? We just saw it. That this term makes DC. So your positive sequence makes DC.
I basically mean we get it like sinusoidal, not the straight line. So yeah, there is a shift of DC.
Yeah. So that's like a DC. When you say shift, it means there is DC. Okay. So here you will have both AC and both DC. And you can see you want to find the frequency. So you can clearly see to find the frequencies, what we can do is, I'll take a snapshot of this. So from here to here, we can find the time period. And so the delta t is your 0.25 minus 0.015. And this is your 0.01, right? And your frequency is 1 over delta t. And so that is your 100 hertz. So as we expected, we got 100 hertz frequency. And we have DC also, right? And you can find the magnitude of DC very easily. So let's do that. So we have this expression for finding the DC component. So it's F cap over this. And so the DC value is in DQ is your F positive cap into e power j phi naught positive minus gamma naught. And we have made these two same. We have made these two equal. So what we get is F plus e power j 0, and we get just ft. We get like this. So there is no imaginary component. So what you see is the DC value is 100, which is the same as your magnitude for your positive sequence. And the Q component mean value, if you see, it's 0. Correct? Is it clear? Okay, so it's getting record, so I think you can I save this? Let's save it so that I can share you these things with your. Let's say like that. Okay, and now I would like to change the part transformation angle. So now I add some phase. So let me add some phase like pi over 2. Okay. So what will let's say pi over 3. Some phase, it can be any phase. Okay. Now what do you see? You see DC, AC, or you see both?
No.
You see only AC. Again, you all are wrong. You see both DC and AC. I have added only phase. Okay. Yeah, it's a gamma node. It's the gamma node I added. So I added just the phase again. So here what it is, your gamma naught is pi over 3. Okay. So you can still see your negative sequence having frequency, but can you see that your now your D value is no longer 50, right? Your D value, the mean value of the D component is no longer 50. It has shifted. And your Q value is no longer, the mean value of Q is no longer 0. It is some DC value. Okay. So now you can understand. So for sure we have AC because of negative sequence. And if you want to see how your DQ change, so your F DQ plus is your F plus. And here, of course, omega 1 is equal to omega 2. So we have J theta positive plus minus gamma naught. And so theta positive plus is your 0. Let's say in this case. Yeah, because our delta we have kept as pi by 3. If you see the MATLAB script, it is this difference is basically going to be minus pi by 3. So we have like plus e power j minus pi over 3, right? And you can find your positive sequence. So your FD is going to be F cap cos pi over 3. And your FQ is going to be minus F plus sine pi over 3. Why you get minus? You know this Euler expression, right? E power j theta is your cos theta plus j sine theta. So I try to just separate these two. So this expression you write in a complex form. So this is your real component. And this is your imaginary component. And so what is cos pi by 3? Cos pi by 3 is 60. So that is going to be your F cap plus by 2. And this is going to be your F cap. What it is? It's root 3 by 2, right? Is it correct? I don't know.
Yes.
Okay. Okay. Yeah. So now you can see it's F plus is your 100. So this mean value is 50, right? You can also see, but I'll show you the MATLAB graph. You can see the mean value is 50. And here, of course, you have to find what is this square root 3 by 2. So square root 3 by 2 into 100. 100 is your magnitude. So it's 86.6. And we have the minus. So if I just try to zoom it, so you can see it is somewhere The mean value is 86.6. You can find the mean and you'll get this. Okay. So never ever think that only D component has value. Q component can also have DC value. It's just the phase difference. It's the phase difference between your positive sequence and your transformation angle, your part transformation angle. Is this clear? Or you have questions? If you have questions, it's the right time to ask. This is very important.
Question. For example, using the Fourier X2, for what I understand, the zero component is the zero component. The 50 hertz component is to be my positive sequence, and the 100 component is to be the negative component.
Do you see 100 hertz component also? Let's say 150.
Okay. But I mean,
so when you have symmetrical signal from your x-axis,
yeah,
then I think you just have odd frequency. Like maybe from y-axis, if you have symmetrical waveforms, then you basically see your third order harmonics. So we are also going to learn harmonics here. So this is the second part. Probably you asked that question there.
okay.
So just add a note that there is a question.
And I have a question. The value that we pay 86, what is by then
Is this that's a DC value?
DC value? And,
DC value due to positive sequence.
and this is the, if you look at the graph, how can we, like, by looking at the graph, can we, it's how we like tell this.
It's the same thing. You just do it the reverse way. So when you see the graph, okay, so when you see this graph, let's say you have given just this graph and you want to analyze this. It's very important for your exam also. So there will be some graph and you have to analyze your graph and then you have to tell few things. Okay. So the thing is, if they give you this graph, let's ignore this one. If you get this graph, then what you can tell? So first of all, you can find the frequency of this. Yeah. So you can find the frequency of this. So you can clearly see there is a AC and DC. So that's the first thing. You see that there is AC and DC. Fine. And you see the D component and Q components are not like the Q component magnitude is not equal to 0. Like the average magnitude when I say, let's say offset. So the offset value is not 0. Okay. So for sure, what has happened, the phase has not aligned. The part transformation angle has not same as the positive sequence angle. Right? If the Q component is 0, what do you mean? The Q component offset value is 0. It means our part transformation angle and the actual positive sequence angle are aligned. So if it is not aligned, then you see something like this. Your Q component can be some value, D component can be some value. If I make, just for example, if I make this phase difference as pi by 2, then you would see the DC value of D component is 0. Can you see the DC value of D component is 0? Yeah, this one. So the DC value of D component is 0, but DC value of Q component is not 0. So never ever think that your D value is only some value. It can be also 0. So that's a good misconception students have, that only D component has some value. But most of the case, it turns out to be fine because you do PLL to find the 3-phase angle, and then you use PLL to do transformation. So that way you are anyway matching the angle. But if your PLL does not work fine, then you will have some issues. So, but mostly PLL works fine. So, but this is one thing you should know. Okay. So you have to see the frequency, you can see offsets, and all those things you can see. And there is one more thing we want to see, but that we'll see in that there is a phase jump also we want to see. And We will see that probably in Simulink, how we do that. Okay, so is this clear? Cool. Now let's imagine. So before imagining, let's put this negative sequence to 0. So let's say we do not have negative sequence. Then you can see this this graph looks beautiful. So just DC. Yeah. So when you make negative sequence 0, that means there is no negative sequence. You just have DC. And when you have some different frequencies, so one moment, I'll make it omega into t. Yeah. So now if you add some fifth order harmonics here, let's say. So now I will add fifth order harmonics, and then just to make things simpler, I make gamma equal to 0. Okay. So now what we have is fifth order harmonics. So now you tell me, there's no negative sequence, there's just positive sequence. Let's say third order, because fifth order actually makes negative. But so let's say we have third order harmonics. There is no positive sequence, there is no negative sequence for fundamental. So what do you see? Whether you see AC or DC or both? It's a quiz for you.
AC.
Okay, one vote for AC.
AC.
Only AC. No idea. So if you feel like there is no idea, you see this equation. So when you have positive sequence, you would have the frequency as omega 1 minus omega 2. So for positive sequence, which frequency will be present in the DQ? Omega 1 minus omega 2. Where omega 1 is your system frequency, omega 2 is your part transformation frequency. And for negative sequence, you should see their summation. Okay. So now you tell me whether it will have AC component only or DC component or both. There's no negative sequence, and the part transformation and frequency is same as fundamental, but we are doing transformation for third order harmonics.
AC.
Only AC. And what would be the frequency? 2 times. Yeah. So that's 100 hertz. For our case, it is 100 hertz. So you would see only AC, and you would see frequency as 100 hertz. Yeah. You can find the frequency again. You can see the time value from here to here. So it is you can clearly see it is the delta t is 0.01, and then frequency you can find as 100 hertz. So now I have again one question. If you see 100 hertz in DQ frame, what it can be? So the question is, if DQ frame has 100 hertz component, what it means, what can be true? Let me give you option. Option A, VABC has 150 hertz component. And of course, for here, your transformation angle is like omega t plus anything. Yeah, let's say gamma naught, and where omega is your 50 hertz. Okay. Omega is your 50 hertz. This is your part transformation angle. VABC has 150 hertz positive sequence. VABC has 50 hertz negative sequence. Both 1 and 2, none.
1 and 2.
I think both.
Both.
Okay. Is this clear? So this is correct answer. It's very easy.
Yeah, if we imagine the equation. Yeah.
That's why I gave you homework to do it. Because if you do it, then probably you know everything then. Okay, so this was very, very easy. So whenever you see some frequency in DQ, it can come from positive sequence, it can come from negative sequence. Remember these things. Okay, so when you see 100 hertz and 50 hertz, the DQ frame, so in the actual system, it can be 150 hertz positive or negative sequence 50 hertz. Or if you see, let's say 200 hertz in DQ frame, it can be 250 hertz positive, or it can be minus 150. It can be 150 hertz negative. You can do the plus minus and then solve these
Can
things.
I ask you, because I'm a little bit confused, when can we have like a DC component? I'm a little bit confused. I don't know.
See, so when you have 50 hertz component,
Yeah.
like let's say when you have fundamental component in your ABC frame, then you do the transformation, you get the DC value.
Okay.
So you see this equation, okay? If in this equation, if your omega 1 is equal to omega 2,
Okay.
there is no frequency, right?
Yes.
So just for positive sequence, forget about negative sequence. So when these two frequencies are same, what you do is you get your positive sequence, you get the DC value.
Yes.
So that's a key. If omega 1 and omega 2 are different, then
I have DC.
no, you have
Omega.
some omega,
Yeah.
and that omega is your AC. When you have omega, it means AC.
Oh, okay. The difference, if the difference is 0, I can have DC.
You have DC because there is no omega. For DC, omega is 0.
Yeah.
Okay, cool.
So
Mhm.
for only the positive sequence, can I have DC?
Yeah, so when you have this thing, so let's make this positive sequence. Positive sequence, this is your positive sequence angle. You can see it's omega t. Here also you can see omega t. This is your transformation angle, the Clarke transformation. So here you have both the frequencies are same. So this is your omega 1. I would like write like this. So let's say omega 1 is equal to omega. So here omega is your 50 into 2 into pi. And your omega 2 is equal to also 50 into 2 into pi.
You wrote 20.
I'm sorry. Is this more clear?
Yes.
Now, if you do the transformation, there is no negative sequence. We make negative sequence 0, just positive sequence. Positive sequence magnitude is 100. So what do you see now? You see DC value. And if I run, you see the DC value, and we see here, it looks dirty. So if you do not want to any image to come again and again, you can do close all. It will close all the images. So you see DC value,
Yes.
and you see 100 as in the D component and 0 in the Q. So it is because your phase angles are same. Like this gamma naught is 0.
So
It means this gamma naught is 0 and this is 0. See, the thing is this, if this value is also 0, then you just get the D component, you do not get the Q component. But now let me make this some value. So I'll add some phase now. So it is pi over 3. Let's say you will get again the DC, but now their values are not like the Q is not 0, D is some value. Clear?
Yes.
Okay, so now you know about frequency and you know about the DC values. So they can be any value depending on the phase and the frequency. Yeah. Anyway, nice question. Is there any other questions? So there is a silence, so I would assume no. And we saw that for DC value, for positive sequence, we subtract the frequency for the transformation. And for negative sequence, we add the frequency. Yeah. So if you see 100 Hertz in DQ frame, so it can be that you had 150 Hertz positive. So if you're 150 Hertz positive and you subtract this 50, you get 100 Hertz in DQ. Yeah. And when you have, let's say, 100 Hertz but negative sequence, 100 Hertz and negative sequence, then you add 150, you get, okay, I don't know, I forgot which frequency I said in DQ. In DQ, which frequency it was? 100 Hertz, right?
150.
100.
Okay, I just forgot which frequency I said, but let's assume this case. Let's say I assume this 100 Hertz. So when you have 100 Hertz, so this is possible. So this 100 Hertz is your can be result of omega 1 minus omega 2 or omega 1 plus omega 2. Basically what I'm trying to say. And your omega 2 we have given it's 50 Hertz. Okay. So it can be any one of these two. So your omega 1 can be omega 2 plus your omega. Yeah, this is your omega 2 plus what frequency is there. So let it put it like this, frequency in DQ frame, frequency in DQ frame. Okay. So the frequency omega 1 can be your omega 2 plus omega in DQ frame, and omega 1 again can be or omega minus omega 2.
Plus DQ.
Yeah. Yeah, let it put it. But that's a little bit then we have to take minus, then we have to use minus symbols there. So this is for let me write this way. You can understand maybe. Just don't want to do any mistakes in positive, negative. So due to positive sequence, your omega 1 can be omega 2 plus omega DQ. Okay. And due to negative sequence, your omega 1 can be omega 2 minus omega DQ. So omega 2 minus omega DQ. So what is omega? Wait. So for 100 Hertz, we would have minus 50. We will have 50. We will have 50. So it should be like this. Sorry. It should be like omega DQ minus omega.
Minus.
Yeah.
So in case we have like omega 1, so omega dq is equal to omega, in case of negative sequence, omega dq is equal to omega 1 plus omega 2.
Yeah. In negative sequence, we have omega DQ equal to omega 1 plus omega 2. Yeah.
So if omega 1 is like minus 50 Hertz.
No. Don't get
Okay.
don't play with the signs again here.
Okay.
If you want to play with the signs, then your So what you said, so when you say minus, if you put minus here, so you mean omega 2 as minus something, right?
Like omega 1, like 50 hertz, omega 2 minus 50.
Omega 2 minus 50, then it becomes 150. That's not correct. So you just put the absolute value here.
Ah, okay, absolutely.
I try to write this equation for absolute value. So for example, your omega dq is 100 hertz. So this omega 2 is your, of course, 50 hertz. So this can be 50 hertz plus 100 hertz. So it's 150 hertz positive. And here we have 100 hertz minus 50. So it is 50 hertz negative.
So we consider only.
So it can be any one of these.
Yeah, yeah.
Okay.
I'm like, my question is like, not regarding this quiz, but my question is like, if in the negative sequence I have like omega 1 50 hertz and omega 2 is minus 50 hertz. In this case, can I have like,
You can cancel that. You can get DC.
DC value, only DC value? That is my.
Yeah.
Okay.
So that way, what you do is your transform. So what his question was, that's a good point, and that is also used for Park transformation. If you go in further and further, you will see the Park transformation for positive sequence, Park transformation for negative sequence. Let's say if you want to control negative sequence, then you need negative sequence value, right? So you can use negative sequence transformation, Park transformation. So what his question is, for example, we have alpha beta f minus cap e power minus j omega 1 t plus phi naught minus. Yeah, we know this value. What if we multiply like this? What if we multiply with j omega 2t and then let's say some angle. Instead of minus, we multiply with positive. Yeah, it's also possible, right? It's just a transformation. It's just some matrix. You can also do this. And in this case, you can make your DC negative sequence value DC. Right? So I think you did something with the Clarke transformation for negative sequence. So if you want to get negative sequence value as a DC in DQ frame, then you can simply multiply with e power plus j omega. Yeah. So I wrote here FDQ minus, be careful. Because here we want to get DQ value negative sequence as positive. So it's everything is possible. It's just a mathematics. You just do whatever you want. And it should be because for your purpose, what purpose you want to do. Okay. So this is to get negative sequence DC value. I would say negative sequence fundamental component DC value. For sure, if you have negative sequence with different frequency, then you will have AC also. Yeah. Any further questions? But this was a nice thing. Okay, so let's move forward. So now you were analyzing things with just one fundamental component, like either one frequency is positive. But now let's imagine you have many frequencies for positive sequence, or you have one frequency for positive, one frequency for negative sequence, how your waveform is going to look like. So that you can understand. So you should also see one graph. So let me see. This is VA, ABCD. So it's called IAL2 and IAL1. Okay. Okay, cool. So now I want to make one more graph. I'll make it in the bottom. So instead of making my x-axis as time, I would like to make my graph with x-axis as V alpha. So now my x-axis is your alpha component and b-axis is what? The beta component. So this is your xy graph. It is what? XY graph. So we already saw long back that it's going to rotate with the same magnitude. So it is basically a circle. It's a circle, believe me, it's circle, okay? You can make this circle by doing these things. And I think there is y limit, x y limit or what? There is no y limit. So let me add y limit. Okay, so you get a circle. So this is circle, okay? You can rearrange this and you can see this as a circle. So this is expected because we already saw in our previous exercise that our one moment, let's see a screen. So that our this V alpha vector, so what we know is our V alpha vector is let's say F alpha vector. So F, this is for positive sequence, it is F cap into e power j omega 1 into t plus phi naught something. Yeah, we know this. So this is in polar representation. It is in polar coordinate representation. So you can see this is a circle. So this represents a circle, right? So this represents a circle and this is your face. So what you have here is your face. And this is your radius. Yeah. So in polar representation, polar complex representation, what you can do is you can represent a quantity like r into e power j theta. This is your radius. And this is your phase. So I think you learn these things from your schools or engineering, bachelor engineering. And you can clearly see the radius is 100. Yeah. And it rotates. So basically it comes from here, it rotates, and again it rotates. So it's make a circle. Okay. So it keeps on making circle. So in one time period, it starts. So it starts from one point. It starts from one point, and then after one time period, it comes back again to the same point. So it takes one time period to complete the circle. And it is obvious this is the phase, and in one time period our phase changed from 0 to 2 pi, right? That's also expected. And you can see that if I change the, yeah, so that is about your alpha beta. And if I increase the frequency of this positive sequence, so I mean I make this positive sequence like 3 times, still you will see the alpha beta plot as a circle. I'm not going into DQ. In DQ we do, in DQ frame one we have the transformation angle, but in alpha beta frame we do not have any angle transformations. Okay, so this is still your the circle, but now here omega is different. So your omega is 3 times the fundamental. So it takes 3 times less time to make a circle. Yeah, and of course your magnitude is same. And you can understand this also very clearly from this equation. I mean this equation. So this is your positive sequence, and you can see it has some magnitude and it has some phase. So this is whatever omega it is, with that frequency the phase will change, but it's anyway going to be circle. Okay, but what if I have both the components? What if I have my 2 components? I want to find the superimposition and then see their graph. So let's talk about harmonics now. Let's talk about some harmonics. So I'll give you just basic fundamental, and then we will get the alpha beta graph again. So what are the source of harmonics in the system, in the electrical system? So what are the source of harmonics? The very basic thing is your switching. You have converters, you switch. You basically do on and off with a different frequency. It can be same frequency, it can be different frequencies, so it makes some harmonics. Like you have, rectangular waveform makes some harmonics. Yeah, so that's a one thing. There can be the harmonics can come from your network also. Like let's say you are working with one converter, and there is far away another converter which gives harmonics, and then that interacts with your system. That's also possible. Okay, so this can be your disturbances from others. So it can be disturbance from grid or another converter, and so on. There are so many possibilities. Like you have the communication or interaction between one system to another system. And yeah, if you wish to inject harmonics into system, you can also do that. So from controls, let's say your control wants to inject some harmonics into the system to meet some purpose, but it's not always happening. But if you wish, you can also inject some harmonic current into the system. So your controls can also do this harmonics. Okay. Like for example, I'm working on MMC, balancing, energy balancing, and then I need some harmonics to balance my arm energies, and then I have to purposely generate those harmonics into the system. Okay, so those are the things. So these are the sources, and there can be many, but I just want you to know that there are some harmonics in power electronics devices. And so what you can do is, so let's see the fundamental component. So you can have VA as VA1. Let's say it is the first order harmonics, which is fundamental. This can be your V1 cap cos omega 1 t plus phi phi naught, and then you have VB1. It's V1 cap cos omega 1 t minus plus minus 2 pi by 3 VC1 . Is this correct? So this is your positive sequence, first order positive sequence fundamental component. Now let's add let's see how the harmonics you can calculate from this. So very simple thing is, for harmonics you basically multiply the phase with the harmonics. Okay. So the general expression for harmonics, let's say harmonics H is is VH cos the whole phase multiplied with H. VBH is equal to VH cap cos, again the whole thing multiply with H, and again the whole angle multiply with H. So this is your general expression for harmonics. So in our system we can have harmonics, we can have fundamental component also. True? So what we can write is, we can write VA as VA1 plus VAH, VB as VB1 plus VBH. Then we can write VC as VC1 plus VCH. Okay. And so this is one way you can do it. So here I have just written one harmonics, but it can be many harmonics also, like just not one harmonics. For example, VA1 plus VA3, you have third order harmonics, you have fifth order harmonics, you have seventh order harmonics, and I have no idea what it is. You have seventh order harmonics, and then and so on.
Isn't the first order is the fundamental?
First order is fundamental. The first order harmonics is always fundamental. So like this, you can have many harmonics. So I'm not writing even harmonics because for basically symmetrical signals, we do not have even harmonics. So those you might have learned in your mathematics in your bachelor's also. Is this clear? So you can have many harmonics in your signals. So let us analyze one thing, so there is one interesting thing, that some harmonics are positive sequence and some harmonics are negative sequence. How you know that? So it's basically this thing, this terms decides whether we have harmonics positive or negative, right? So I mean these terms decide whether we have positive sequence or negative sequence harmonics. If we get here plus 2 pi by 3 and here minus 2 pi by 3, it means negative. If we get here minus as it is, if we get as it is, then what we know is it is positive sequence, right? If you want to know whether it is positive or negative sequence, you see basically B and C phase, and you see their phase lag. Which one is leading, which one is lagging? Either B is leading or B is lagging. So let's see it when the H is equal to 5. Let's start with 3. So when H is equal to 3, your VBH, VB3 is going to be V3 cap cos 3 into omega t plus phi naught minus 2 pi by 3, right? And if you solve this, so what you can write is V3 this into cos 3 omega t plus phi naught, and then this becomes minus 2 pi. This is interesting now. So this becomes minus, and it is, so it makes asymmetrical or what? So it's 2 pi by 3, this gets 2 pi, and this is 0, 128, 240, and then it is 0. Okay. So what we can, so we can see this is as a, this as a 0. And then VC3 this is omega t plus phi naught, and then we have my C as plus 2 pi by 3, and then we can see this is as V3 cos 3 omega t plus phi naught, and this gets 2 pi. Okay. And I think you can see that this is your, so this is going to be same as cos 3 omega t plus phi naught, right? And this is again going to be cos 3 omega t plus phi naught. Oh, it's interesting that you see the similar expressions for your the third harmonics. Yeah, so it makes basically the zero sequence. So it makes only in third harmonics basically makes the zero sequence component. And I think you use, so this, yeah, and I think you use this for your common mode voltage. Okay. And you have you heard of common mode voltage? No, right? Okay. So have you heard the supersine triangle PWM? Supersine triangle PWM, whether you add the third order harmonics into the voltage to read, you will learn that in power electronics lesson. So you add third order harmonics, and you can see you can basically get the phase, and the it looks the same. It looks the same voltage for all the three phases. So it is basically making zero sequence. So third harmonics is like making your zero sequence stuff. So let's see fifth order harmonics. So for fifth order, so I will just write a comment. So here VA3 is very simple. So it is your 3 omega t plus phi naught. And what we see from conclusion that VA3 is equal to VA2 is equal to VB3 and then VC3. So I would say zero sequence yeah, but this is interesting. I try to do this math here and it turns out like this. And then let's see our fifth order harmonics. So VA5 is equal to V5 cap cos 5 into omega t plus phi naught, and VB5 is your V5 cos 5 omega t plus phi naught minus 2 pi over 3. And if you simplify this, you can write like this. Oops. So if you simplify this, you can write it like it's like 10 pi over 3. And now we want to solve this 10 pi over 3. So you know that if we subtract 2 pi from this, it is not going to do any change to the phase thing because it's just a rotation by 2 pi. And then we can solve this, we get 4 pi over 3, right? So can I write this as VA cap cos 5 omega t plus phi naught minus 4 pi over 3? Is it possible? So you know these things, right? Cos 2 pi plus theta is same as cos theta. So I just try to subtract the 2 pi from that angle. And if you see this xy axis, so this 2 pi by 3 is basically 240 degree. So it should be somewhere here. So can I write this 4 pi by 3? So this 4 pi over, this is 4 pi over 3. Can I write it like this? Plus 2 pi over 3. Or maybe like this, minus, is this fine? I write 4 pi over 3 as minus 2 pi over 3. So from here, it's the same thing, right? You go 240 degree anti-clockwise or you go 120 degree clockwise. And of course, this minus multiplies and get positive. Oh, sorry, it's 2. So now you see interesting thing. One moment. Yeah, it's again V5. So do you see one interesting thing? Your B sequence is leading by 2 pi by 3 now. Your B voltage for fifth order harmonics is leading by 2 pi by 3. And you do the same math for the C phase. You can do by your own. I'll just write the result. You will get like this. And of course, you have your A as this. So these makes your negative sequence. So your fifth order harmonics makes negative sequence, 3-phase system. You are clear how we got this minus 2 pi over 3, right? Everyone is clear? Yeah. So if you know how to get this one, then probably you will also know how you can get this as minus 2 pi over 3. Okay. Okay. So this makes negative sequence. So if you want to see the DQ transformation for fifth order harmonics, then what you would expect in DQ frame? AC component.
Frequency of 5 times the frequency of the generator.
Not 5 times, 6 times. Because for negative sequence, it's omega 1 plus omega 2. Omega 1 is 5 times, omega 1 is 1 time, so it's 6 times. So you see, 6 times means your 300 hertz. Okay? Okay. Let's see the seventh order harmonics. So, So VA7 is your V7 cos 7 into omega t plus phi naught. Yeah. VB7, I really want you to do the calculation, but what you would see that this is going to be your positive sequence. We will do it very quickly though. So you know that we have to just find the phase, this phase for your to know whether it is negative or positive. And you can see how we got this one. So let's do it. So let's see how we got this one. So what we know is 7 into so it is minus 7 into 2 pi over 3. So you have to basically prove that this is equal to minus 2 pi over 3. And you can again subtract 2 pi. So you get like, so this is your 14 pi minus 6 pi by 3. And you can see it is your 8 pi over 3. It is still greater than 2 pi. We again subtract 2 pi. And you see it is 2 pi over 3. So this is minus, so we basically I basically remove that one. That is more easier. So you get like here 8 pi minus 6 pi over 3. So it is 2 pi over 3. So what you know is 7 into 2 pi by 3 is same as 2 pi over 3. Okay. So that is why you have this term as the same. So these things makes positive sequence. Okay. And now you go to 9th order harmonics. So I'm not going to write that. That would be too much. So 9th order would again make your negative sequence. 11th order would make positive sequence. 13th order will make your negative sequence. And 15th order will make positive sequence. So you can find a general formula from this. So you can see after every one alternative, it's making positive or negative, positive, negative. So you can find a formula from this, right? Yeah. So I leave that formula for you, or you can simply remember one thing like 5th make negative, then 6th, 7th make positive. Then you can alternatively also see which makes what. Do you have any question now? No. Okay, so now let's see some graph. So now what we want to do the simulation is we want to add positive sequence and your 5th order system, 5th order harmonics. And in the second part, we want to add the 7th order harmonics. And we want to see their alpha beta plot and DQ plot. Okay. So now we no longer analyze just one frequency. We want to analyze 2 frequencies, and then we want to see their alpha beta plot. Okay. So let's see how does it look. So let us first add harmonics. So we do not have any harmonics. So I will use this negative sequence as a harmonics basically. So let me write VH. H means harmonics. And here I multiply with H. Is this fine? So now this is more like a harmonics, and we make this harmonics as h. I make this magnitude as 20%. Okay. And then I add one more variable. So that variable is like, let's say h. So your h is equal to, let's say the fifth order in the beginning. Okay. So I'm just wondering, if we make third order harmonics, then do we see any change in alpha beta frame?
No.
No,
It should be, it should not do any change. You should see a circle still. Yeah, because we know third order harmonics is equal in all the phases. So you can still see this, the same graph when I make this as 0 also, you would see the same graph with 100 magnitude. Yeah, it's the same. It does not matter if you have third order harmonics, you will not see anything in alpha beta frame. Now I have added fifth order harmonics. So this is your fifth order harmonics. How many of you like flowers? We'll have one flower. Is this nice flower? Okay, but there is a mistake. I should make this as minus, this as positive. Yeah, now it is actually positive sequence angle. So yeah, it should look like this actually. So this is starfish, right? How many aces are there? How many A's can you count? When I say A's, it means these. How many are there? 6. But it's a fifth order harmonics. We have 6 A's.
The fundamental.
It's a relative frequency. Yeah, it's a relative frequency because you know that the fifth order makes negative sequence. And when you want to find the relative speed, it's omega 1 minus omega 2. And so what happens here is, this is your alpha frame, this is your beta frame. This is your fundamental component. So this will rotate with some magnitude, right? Like it will rotate with the same magnitude and it will make a circle. I know it's not a nice circle, but let's say, so this is your fundamental component. So V positive, V1, let's say, okay? V1 vector. So this is your fundamental component. And if you want to see your fifth order, so one moment, this rotates like this with omega 1. And now you want to see the fifth order harmonics. So fifth order harmonics would also be, it also be somewhere here, but its magnitude is 20%. So it will be like this. And it also makes circle, but it rotates like this. It rotates with 5 omega 1. We know that negative sequence rotate clockwise and the positive sequence rotate anti-clockwise. So this is how your negative sequence rotate. And this is how your positive sequence rotate. We saw this in the first exercise. I know it's very long, but probably you remember. Is this clear? And you want to see the relative speed of these two. Because now what we have is, this is V5 basically. Now what we have is our V vector is basically the vector summation of these two vectors. Because now we have the first order harmonics and we have the fifth order harmonics. So we should superimpose those to get the final alpha beta plot. Yeah. And this is since it's a superimposition, and then we get this curve, and you can clearly see they are moving away from each other. So their speed adds up to get the relative speed. So your delta omega is your omega 1 minus omega 2. Let's say omega 1 minus omega 5. Omega 1 is positive, so it is omega naught. Let's say omega 1 is your omega naught. Omega 5 is your minus 5 times omega naught. So when I write minus, it means it's a negative sequence frequency. Okay. So this is your vector. So it's like that. It tells you the direction. So omega naught minus omega naught minus 5 times omega naught. So it becomes 6 times omega naught. So this is your relative frequency. So I would say relative angular frequency. Okay. And you want to analyze you want to see it also one way, so you can do like this. So let's say this is your alpha beta graph. So this is your fundamental component, and on top of that, you will have initially their phase. The initial phase for both is the same. So in the beginning they will be like this, and when they start rotating, so let's say after some time they come here. So this fifth order so this is in the beginning, and the fifth order after some time. So this rotates in this direction, and this fundamental rotates in this direction. This is with omega naught, this is with 5 omega naught. So what would happen is this red one would be somewhere here. Yeah. And then you will see the resultant as black is good. So then you will see the resultant like this. So initially it was here, then it came here, and then after again some time, what you would see that this is out of phase. It means the red one has completely gone negative, and then you would see the resultant is this. So it is like this. And then what happens the next time? Next time again, it is like this. Then it would be something like this. And then we will have resultant like this. Okay, so it starts increasing now. And after some time, what would happen, that you will see it will be again in phase, and then you will see the maximum magnitude. Yeah. But the phase angle difference I have drawn is for sure not up to the scale, because I wanted to just show you some graphs in between. So what is happening, and you can actually find after how much time, or the phase angle, you will get this minimum value. You can actually find, or you can find this time period also. So what we know is, delta omega is basically your omega 1 minus omega 5, which is equal to 6 times omega naught. Okay. So what you know is, it is 6 times omega naught. So it means if you want to find the phase angle difference between those two. So what I mean is, so this is your this is your V1, or let's say F1. This is your F5. This is if you want to find this delta theta. So delta theta is your basically delta omega into time. Okay. And for sure you can write it like 6 omega naught into t. 6 omega naught into t. And what happens if delta theta is equal to, pi, so you would see the negative peak, you'll see the lowest amplitude, right? So pi means what? You have your vector like this, positive sequence, and the negative sequence vector like this. Yeah, or you can imagine like this. This is a negative sequence, and this is your positive sequence, and their angle is pi. Angle difference is pi. So this way they make the least magnitude, right? So here we'll have the least magnitude. And when this is equal to, so equal to 6 omega naught t is equal to 2 pi. So 2 pi means they are in phase. So their resultant will be higher. So this makes your maximum magnitude. And from here, of course, you can calculate your time. But this is just for your understanding. And actually, my supervisor has made some graphs to explain it. So I can show you that thing. This is the same graph you saw, right? So what happens is, in the beginning, okay, I do not want to see this. So in the beginning, what we saw is they are in the in phase, so their magnitude is maximum. And after some time, what you would see that they are basically facing opposite to each other. So they are out of phase. So you can see the positive sequence is pointing upward and the negative sequence is pointing downward. So it makes the least magnitude. Okay. And like that, you can see again after some time you would see the maximum magnitude and so on. So you can also try those. So you should actually try this, because if you want to understand this, then you should draw some diagrams like this, and you should try to understand what I have tried to do it here. But you would see the graph like this, and you will have 6 ages. Why 6 ages? Now you know, because their relative speed is 6 times the fundamental frequency. So you will have 6 ages. Okay. What if you have the 7th order harmonics? So I would like to draw on the same graph, so I'm not closing the graph. So what will happen if you have the 7th order harmonics? How many ages you will see?
Also 6.
Also 6. So will it also look like this?
We have to change the by
No, like I changed this h equal to 7. So it's seventh order now. And now I want to draw it. And I did not close the graph. Okay. So whenever you make some graphs like this, then I would suggest you to do one thing. So you have not written figure here, right? For the subplot. So whenever you make some graph, try to write here figure and give some name. This way it will always plot on the same graph. Okay, so let's do it again. So we will draw for fifth order harmonics. So we got this graph. And now we draw the seventh order for the same thing. So I'm not closing this graph, so it will draw on the same graph basically. Interesting. But the thing is, it has again the 6 edges, right? Can you count? Can you count it? One, 2, 3, 4, 5, 6. So it again has the 6 edges, but it looks different, by the way. So when you see some flower, it's like positive sequence. When you see something going like this, it's negative sequence. Yeah.
I think I have understood.
Okay. So this is in alpha beta frame. This is in alpha beta frame. Okay. So let's understand the seventh order. So there's one thing I would like to mention here, which maybe students don't mention, don't see it very quickly. So what we know is that our fundamental is rotating this way, and now our seventh order is rotating also this way. This is your 7 times omega naught. This is omega naught. So if you want to find the relative angle, so I mean this. So let's say we have here F1 and this is your F7. So this is your F1, this is your F7. So what you can do is I'll draw it other way. Wait. So let's say at moment, this is your fundamental component. And here we have your seventh order component. So this is your theta 1, theta 7. So you want to find this delta theta. So this is your equal to theta 1, theta 7 minus theta 1. Yeah. And you can write theta 7 as your 7 times omega naught into t plus some phase. I'm ignoring the phase, okay? So let's assume your phi naught is equal to 0 minus your 6 omega, sorry, not 6, it is omega naught t, and it gets you 6 omega naught t. So again, your relative speed is basically 6 times omega. And you can also imagine like this. One is rotating with the 7 times omega naught and another is rotating with the omega naught. So your omega 1 is 7 omega naught, omega 2 is your omega naught, and omega 1 is actually omega naught, and omega 2 is omega 7 is like this. And for sure, omega 1 minus omega 7 minus omega 1 is your 6 times omega naught. So this is your delta omega. Okay. Yeah. And so again, we will see 6 aces and you can find the angle like this. So there is one interesting thing. If you see the angle difference between the fundamental and the harmonics for 5th order and the 7th order, their angle difference is always the same, right? It is 6 omega naught t for this, and this is also 6 omega naught t. Yeah, it is just that for one it is positive, for one other it's negative. So here, yeah, if I just do this, so like I think you know what I try to mean. So let's say at any moment this is your fundamental, this is your V1, and so this would be your V5. And again, this, if the magnitude is same, let's say this is your 30 degree, then again with the at some time, your V7 will also have the same angle difference, right? If you see in the time domain, it will have again the same angle, because it's the angle difference equation for both. The magnitude is again the same, right? So yeah, so if their angle is same, and if I assume that their magnitude is also same, then their resultant magnitude also be same, right? Is it more apparent? So if you want to find the resultant, you would see this is one resultant, and for this also you would see this resultant. So their resultant will be the same, but it's just the phase, the phase of the resultant is different. Okay, so I would like to name these again. So let's name this as your V15, and this one as green one, V17. So what I can say is 15 is equal to V1 vector plus V5 vector, and V17 is equal to V1 vector plus V7 vector. And yeah, and I assume this. So with this assumption, what I can say, V15 magnitude is equal to V17 magnitude with respect to time. With respect to time. So this is the same thing. So it will be same magnitude for alpha and beta frame. No, same magnitude if you want to find the alpha square plus beta square and the square root 2. But why do we see some two different shape? So this is for 7th order, it looks like this. And for 5th order, it looks like this. So why there is a different shape for these? You can clearly see that their maximum and minimum points are the same. The maximum and minimum points are the same, but the trajectory is different. Why you see like this, even though their magnitudes in time with respect to time is the same. So there is a very basic thing. So this equation I wrote is with respect to time. So if you draw this with respect to time, you would see the same thing. But here, your x-axis is not time. Your x-axis is the alpha. The alpha. And when you see the alpha, you see that this fellow makes more alpha and this fellow makes less alpha. Yeah? So let's draw it again. So we know that this makes your V alpha 15 and this makes your V alpha 17. And you can see that in this case only I'm saying, okay, not all the cases. In this case, V alpha 17 is less than V alpha 15. And I would like to take a screenshot of this. And you can see, so V alpha 7. So it means if this has some magnitude here, so it will have higher alpha, which is this alpha. Okay, let's choose some point here. So this is your V alpha 15. And at the same magnitude, if you try to find the same magnitude, it will have some magnitude here. Okay, the magnitude of the both should be the same. It means this vector and this vector, this is V17 and this is V15. So these two magnitudes are the same, because here V5 magnitude and V7 magnitudes are the same, right? We choose the same magnitude for harmonics. So these two magnitudes are same, and so for sure what will happen, your V alpha 17 is less. This is just one extra information I gave it to you. It's not very needed, but you can clearly understand that even though with respect to time they will have the same magnitude, but in alpha beta frame it looks different. So whenever you see some flower like shape, it's positive sequence. If you see some shape like this thing, it's a negative sequence. And then you can know the frequency of the thing, right? So if I show you this graph, let me okay, there is one mistake, sorry. This ninth order does not make anything. So it's again zero sequence, sorry. This ninth order is zero sequence because it's a multiplication of 3. So multiplication of 3, it's going to make zero sequence. This is going to be negative, and this is going to be positive, and again this is going to be 0. Okay. Yeah, so that was one thing. So I made this 9, and you again see a nice circle. So there is no negative or positive sequence. And I try to make this as not 10, 11. So is this negative sequence or positive sequence? Negative. And you see it is going from below. And make a positive sequence. It goes from above. So you should actually plot these graphs and get familiar with this. Okay. So this blue one is for the 11th order, and this red one is for the 13th order. And you can see for positive sequence, it goes from top, and for negative sequence, it goes from below. So you should do this and practice and remember these graphs, because we can give you this graph and we can ask you which harmonics it is. So you should be able to tell it. So it's one of the important graph you should know. Okay. So this, I think you are clear about harmonics. Now there is one thing we do, and then we go for lunch. And after that, we start with the Simulink. So enough with the MATLAB script. I think you are more confident in the MATLAB script now. You can do so many changes. So now let's analyze one thing. The fault analysis. So you know there are faults in three-phase systems. So which are the faults which you know? So you know symmetrical and unsymmetrical faults. Yeah. So there is a symmetrical fault. And there is unsymmetrical fault. So when I say symmetrical fault, it means we have three-phase system and they all are short. So this is your A, B, and C, and they all are basically short. Let's draw with a red line. It feels like it's short. Okay, so there is a short in all phases. Unsymmetrical means it can be short circuit. It can be short circuit between one phase to another phase. So like there are many faults. So let's list it out. So in this we have one phase E fault, two phase E fault, and then we of course has two phase fault. Yeah. Is this? Yeah, I think so. So we have like two phase E. So this means two phase. Oh, sorry, not two phase. One phase to ground fault. This is two phase to ground fault. And this is two phase fault. So if you want to draw the fault for this, so this is your ABC. So let's say only one phase has faulty. So only one phase has got connected to the ground. So this is your one phase E fault. The two phase E. For two phase E, there is two phases has fault and they are connected to ground. And two phase fault is you have fault between two phases, but it's floating. It's not connected to ground. Okay. So this is also your fault. Okay. So now you would like to see the transformations for during the faulty conditions. So yeah, so when you have a symmetrical fault, then you would see your voltage will dip. Basically, your all DQ voltage will dip because there is no magnitude for the voltages. But in unsymmetrical faults, we would see some unusual things in the alpha beta, like some different things in the alpha beta frame. So to simulate the fault, what we can do is we know VA equal to V plus cos omega t plus phi naught. You know, like this. And then what we want to do is we want to, so in the fault, basically one thing will get zero. So if you have fault in all three phases, then all three can be zero. If we have fault in one phase, let's say B phase, then this can be zero. If we have fault in the C phase, then C can be zero. If we have fault in A and B phase zero, B and C phase zero, then it both can be zero. And when we say fault, it's not necessary it has to be solid fault. It can be some fault with some impedance also. So when there is an impedance, it makes some voltage. So it's called low voltage ride through. Okay. So it's called low voltage ride through. So that means your fault voltage. So during the fault also you can have some minimum voltage. Let's say 20%, 40% of the nominal voltage. So that is your low voltage ride through. I think you have heard this in your power systems lecture. It's called LVRT. low voltage right through. So if you are a power engineer in power systems also, if you design something, your system should be able to sustain this low voltage right through. It means your three-phase grid voltage suddenly drops to some voltage, but after some time it will come back again. So your system should be able to sustain that thing. So in faulty locations, faulty conditions also, you should protect your device. So let's do it. So what I do is here, I basically add some code here. So with this, can you, so you can see that the fault is in B phase is 0, right? Like there is a fault in B phase because I made this VB equal to 0. Is this clear? This makes B fault. Of course, this will also execute, but I'm bypassed it. So now I can comment this if you like. It's the same if it's there or not. So now how you will see your, then how the graph would look like. Let's see. So that's a problem because it's just a one vector. So we need some number of time. So I will just multiply this with 0. It showed the error because it's just a one element. And we need so many we need a matrix basically to do the calculation. I do not expect the error now. It says, okay, sorry, I should uncomment this. Yeah. See like this? So I think there is harmonics also. That is why it looks funny. But it is no longer a circle. You can clearly see it's no longer a circle. So it is like this. So when you have fault on the B side, then you would see your alpha beta graph looks like this. And you can draw this graph the same way we did with the positive sequence. I mean, in the beginning we did this. We did these things, right? In the beginning. So now there is no B phase. There is just A and C phase. So you will just take A and C and you draw this graph. So you will see the magnitude will be maximum here, and other places it will be minimum. Then again it will be maximum somewhere here. So it will not be again 60 degrees. Remember, it will be somewhere here. You have to do these maths. So I will leave that to you. But you would see some shape like this. Okay. Let me remove the harmonics. Now I want to close the graph and I remove the harmonics. So you see like this. Now let's have fault not in the B phase, but in the C phase. Okay, so now we have fault in C phase. You see it has changed the shape. So now it is in the C phasor. So if you see the phasor diagram, right? If you see the phasor diagram, this is the phasor for C, right? The phasor diagram, not the state space diagram. So this is your state space and this is your phasor. So it is, you can remember like that, but it's not like that. You have to do these things to get your actual shape. But you can basically do that to remember for B and C phase only, by the way, B and C phase only. If there is a fault in A phase, then you see how it looks. It is not along A phase, remember, it is vertical. It is somewhere, it looks like vertical things. Okay. So you have to know these things, and in exam for sure we can give the shape, and then we can ask you or tell us which fault it is. So which fault it is? It is symmetrical or unsymmetrical? Unsymmetrical because there is there is just fault in one place. And which phase we have fault? The phase A. Okay. So let's have a symmetrical fault. Everything 0. What do you see? I'm expecting some dot, but probably we cannot see the dot. Okay, but as I said, you the low voltage right through. So let's say we have some magnitude. It's possible. This is also fault. So you will see a circle, but with the less magnitude. So this is which fault? Yeah. If you see circle with a less magnitude, for sure it is symmetrical fault. And now let's make the fault in only A phase. So now it's the same thing, but now there is a fault in only A phase. So this is, I have not made it 0. It is just some value, but still you see the shape is similar. You can see on these values, it is less than 100 and upper value is like close to 100. Okay. Okay. And the same thing you can see with this. So B phase, it is expected to have like this. So for B and C fault, you can remember like your phasor diagrams. Okay. And let's imagine a case where we have the fault in one of the phase, but the 0 sequence is 0. If you see here, your 0 sequence is not 0, right? If you see this graph, here you see some 0 sequence. This is your 0 sequence, and it is not 0 because it is expected, because in symmetrical system, then only your 0 sequence is 0. It's unsymmetrical. So in unsymmetrical, we will have some 0 sequence components also. So that is why there is no 0 sequence. There is 0 sequence, but if you remove 0 sequence, how you can do that? So I keep the VA same, but VC I make it like minus VA minus VC, VB. Now my 0 sequence is 0. So I basically keep the VA as the same as VB has a fault, and you can compute the VC by making 0 sequence 0, because the 0 sequence is summation of all divided by 3. So now you can see summation of these voltages is 0. So for this also you would expect graph similar. Yeah. So it's again in the same. Oh wait, yeah, the fault is on a B side. So you see it's also pointing in the similar direction, right? Of course the phase changes, but you know the shape is like the phase of this changes, but it's again pointing like this only. So the pointing direction is same. And if I do the fault in B, in the C phase like this, so I make this as a C, and then this I make as a B. So now we have fault on the C side. And again, we see the similar shape. Okay. So if you may have 0 sequence or may not have 0 sequence, and what we would see the similar shape. So probably will not bother you much about the magnitude, because this magnitude changes when we do some fault with some voltage, but maybe we can give you the shape and then we ask you which fault it is. So you have to also see whether it is symmetrical, unsymmetrical, and then whether it is, which phase it is. Okay. Okay, so this is So the sub operation, harmonics, faults. Yeah, looks like everything is covered, but now we just have to do the same thing in Simulink. Okay, so now we have to move to the Simulink part, but this is all about basically the transformation theory. So you can see that we did a lot of test case to show you different things in alpha beta frame, DQ frame, and so this is just to make you familiar with the DQ transformation, the transformation. So there are so many things. So people think that DQ transformation is very simple. You just get DC component in the DQ, that's it. But there are a lot of things. When you have harmonics, when you have negative sequence, then you have some frequencies. And so those things you should be aware. You should be aware when you are designing things. And when you're designing your PLL, you should design your PLL nice so that you just get the positive sequence angle. If you design your PLL, if you do not design your PLL nice, then you would get also noises in the angle and in the frequency because of your harmonics in the system. So you should know how to filter those things also. But it depends how much magnitude of harmonics you have. If it's less, it's okay. But if it is really more, then you have to add some filter to get your positive things. So this is more about making you confident about transformation. Okay. So you should really practice this. You should see all the cases which we tried, and it's recorded also. So that's a good thing. You can keep on playing this. I will upload this video. And then, yeah. So you should practice this by yourself. At least once. As many times you want, but at least once. Yeah. And then the next part is our Simulink, and we make a break for 35 minutes or maybe 40 or 45 minutes. So we try to do lunch quickly, and we would meet here by 2 o'clock. Yeah, we try to meet here by 2, let's say 2:05, and then we will continue our session. So let's pause this.